But he's very happy about the fact that I'm not Fred Cohen. Actually, I'm sure Nigel is thinking, well, why don't you apologize for being Tony Bahri? But anyway, the reason that I am able to give this talk at short notice is that I've lost weight. So on the plane, I was able to open my computer, right, without the seat pushing it into my stomach. So it's the benefits of weight loss. And then as I was running over here in the rain, I slipped and I almost killed myself. So somebody would have had to have prepared a talk in 2 minutes, which would have been a much better effort than mine. Well, Fred was going to talk. In Fred's talk, he was going to report on the results of his student, Ali Al-Raisi, and so I thought I would incorporate that into my talk. So although Fred is not here, I hope you will get a flavor of the things about which he was going to speak. And I too would like to thank the local organizers. It's obviously a class operation. I would like to thank Dong Yup, Su Yong Choi, Sun Jong Park, and Tomo Matsumura. Very good work, and thank you very much. Okay, so many of you will know the definitions, the elementary definitions that I'm about to put up here. I hope you'll forgive me for that, but it will save subsequent speakers who decide to talk about these topics a lot of work, because I will have already said what things are, taking up my time to do that. So I hope those of you who are experts in the audience will manage to stay awake a few minutes, or not, while I just mention some elementary definitions, if that's okay with everybody. Now all I have to do is work out how to go to the next page, hoping there is a next page. Yes? Okay, so I am going to describe theorems about what have come to be known polyhedral products. Now, I think of polyhedral products as familiar spaces from a different point of view. Now, a polyhedral product is a subspace. It's a subspace of a Cartesian product, a natural subspace of a Cartesian product. There's no gluing that involves any sort of twisting whatsoever. And this subspace is defined by a simplicial complex, which generally we agree to call the dimension of the simplicial complex n-1, and the simplicial complex has m vertices. And in addition to that, one is given a family of CW pairs. For my purposes, I would like them to have a base point. That's quite important. And there is one CW pair for each vertex. And so from this information, the simplicial complex and this family of CW pairs, we make a topological space that sits inside a Cartesian product, a very simple space. It turns out has been studied for many years under a different guise. Now, the topological space is defined as a colimit over a diagram that's specified by a simplicial complex. Now, if you're a bit shaky with those words, it's a very simple object. So it is a Cartesian product. It's made from pieces, one piece for each simplex in the simplicial complex, and each piece is a Cartesian product of topological spaces, and it's a product of Wi, where Wi is the big space Xi, if I is a vertex of the simplex, and it's equal to Ai if I is not a vertex of the simplex. So the simplices are indexing which Cartesian products occur, and then I make the polyhedral product by taking the union of all those Cartesian products, right? There are no fancy gluing maps. It's a very basic construction. Let me just give you a couple of examples, if I might. Here's a trivial example. This is a simplicial complex that has two vertices, just two disjoint points. So I take two pairs and I choose to take a 3-disk, a 2-sphere, a 2-disk, a 1-sphere. So this is going to be the union of two pieces, one for each of those simplices. Each simplex has one point. So the first one has 1 in it. So it's the disk, it's the x1, cross the A2, which is S1. And the second piece will be the A1, which is this S2, crossed with the x2, which is D2. And when I take their union over the part of the Cartesian product indexed by the 0, the empty simplex, I get the boundary of the 5 disk, which is a 4-sphere. But the
no base point
no base point so far. So the beauty of the subject is that this line contains more information than that, right? That's the whole point. So the second last line is more information than recognizing it as the 4-sphere. Okay, let me do another trivial example. If I take here the same simplicial complex, 2 disjoint points, and here x1 and x2 are the same, a1 and a2 are the same, and cc star, then this time I get the complement of a subspace. So it's a complement of an arrangement, the particularly trivial arrangement in this case. But so here, these spaces, they arise in the complements of subspace arrangements. Here's another trivial one. Here's a simplicial complex with an interval and a disjoint point, and I take every xi, ai, there are 3 of them because there are 3 vertices, to be the one disk and the boundary, 2 disjoint points. In this case, my polyhedral product is going to be a subspace of the Cartesian product, 3-fold Cartesian product of an interval, and that is a cube. And this simplicial complex indexes this subset of the boundary of the cube. So that's quite a complicated topological space, right? This is a complicated topological space, but it's indexed very trivially by that simplicial complex. Now, had I taken the full simplex, of course, I didn't point this out, but if K was the full simplex, then you would get the whole cube, right? So the whole simplex gives you the whole Cartesian product. Any non-trivial simplicial complex gives you a subset of a subspace of the Cartesian product. And I think I have one more example. Now, these are the examples which are studied by Ali Al-Raisi, Fred's student. In this case, the simplicial complex is the boundary of an n-gon. I shouldn't have said n-gon. It says boundary of an n-gon. And my x and a, they're all the same, d1 s0. And in this case, this polyhedral product is a closed orientable surface, and that's its genus. And it was... actually, I prefer to point. Thanks very much. And the laser light drives me nuts. I feel like a cat. And if I start playing with a laser light, I'll start chasing it like a cat. Some say that's the way I lead my life. Okay, it was pointed out to us by Alex Sushu that this is a result of Coxeter, an old result of Coxeter. So this is another example of a polyhedral product. And I'm sure that many of you in the audience know that these spaces play a central role in toric topology, toric geometry. And if I put C and C star there, algebraic geometers will be familiar with the Cox spaces. So, but this won't be a story about toric geometry at this part of the lecture. Okay, so I can make the same construction as I just did, but instead of using the Cartesian product of spaces, I use the topological smash product of spaces. That I need a base point for that. And so this time, I can do the same thing, and I get a topological space, which I'm going to call Z hat, as you can see up there. And that will be a subspace not of the Cartesian product, but of that smash product there. And in fact, it coincides with the image of the polyhedral product under the map from the Cartesian product to the smash product. And this is what I call the smash polyhedral product. It's a closely related space. Okay. Now comes a standard construction in homotopy theory. It's known as the James construction. Many of you, I know, will be familiar with it. I hope that the experts in the audience will indulge me just so I can say a few elementary things about the James construction. So the James construction is on a topological space that has a base point, and it's traditional called the base point E. And the James construction makes a topological space from the disjoint union of the Cartesian powers of Y. So I take the disjoint union of all the Cartesian powers of Y, and I join them together with an equivalence relation where the equivalence relation recognizes whenever the identity appears, I glue that to the one below without the identity. It's a standard construction. It makes a topological monoid, and in fact this is the free monoid generated by Y with unit E. So this is just a construction on a topological space Y, and it produces another topological space. And the reason that it's important in homotopy theory is that it's homotopy equivalent to starting with the space Y, doing topological suspension to it, and then taking the base loop space. And so that property of the James construction makes it indispensable in homotopy theory. So that's the James construction. Now, I'm getting closer now to the work of Al-Raisi. Now, keeping the James construction in mind, there's another topological construction. If I take a Cartesian product of X with itself, and I suspend it, I do a topological suspension to that Cartesian product, it produces for me the suspension of a wedge of smash products of spaces. So for example, what does this, it looks very complicated what I've written there, it looks very complicated, but all I'm saying is this, is if I take the suspension of U cross V, then that's homotopy equivalent to the suspension of U, wedge the suspension of V, wedge the suspension of V smash U. That is a standard identity in homotopy theory. The Cartesian product decomposes stably. That's what that says up there, but I'm taking an n-fold Cartesian product, and its M is just an indexing set 1 to M, and I is a subset of 1 to M. So it's all possible wedge summands, all possible smash products. Now, you notice that big H goes from a suspension to a suspension, so I can take the adjoint map, and the adjoint map will go from the space to loops on the suspension of the right. So this is the adjoint, the functorial adjoint of the space on the top. And now, since I recognize this as the James construction, because look, it's loop suspension of Y. A loop suspension of Y is J of Y, right? So I have such a map. I have such a map from the Cartesian product into the J construction of all the wedge summands from the stable splitting of a Cartesian product. So these are standard constructions in homotopy theory. Okay. Now we can actually say what this map is, and it just takes a point x1 to xm to a product. Remember, this is a monoid now, so I just take all possible wedge products and multiply them together, and that is the map. Now, on both sides of this, there is an action of the symmetric group on M letters. This is an M-fold Cartesian product. All my Cartesian products are M-fold Cartesian products. And so there are actions of the symmetric group, and this map is equivariant with respect to that action of the symmetric group. Okay. Now, there is a theorem that mimics this one, right? Remember I told you this theorem here. Now the polyhedral product is a subset of a Cartesian product, right? And it turns out that this splitting has an analog in the world of polyhedral products, right? It's exactly this, more or less. It's this splitting here. And that tells me that if I take the polyhedral product and I suspend it once, then it breaks apart into a wedge of spaces, and those are the smash polyhedral products. They all have, instead of Cartesian products, they have smash products. So that is a splitting theorem for polyhedral products, which has many interesting consequences. And this wedge is over all subsequences of M, all right? All subsequences of M. Now, and also there is a new simplicial complex here, K sub I, and K sub I is a sub-simplicial complex of the original simplicial complex, and it is what is called the full subcomplex consisting of all simplices which have all of their vertices in I. So it's a sub-simplicial complex, the full sub-simplicial complex, indexed by the vertices determined by I, and that's what this splitting does. Now, why? I mean, it doesn't do any good to have a splitting if you do not know what the pieces in the splitting are, right? I mean, so what? But the answer is that there are techniques which allow one to identify what these pieces are, right? So you know what those pieces are as topological spaces, particularly up to homotopy. So that's a splitting theorem for polyhedral products. So I think you can probably guess where this is going. Now, those observations I made about the James construction on a Cartesian product and its equivariance, that extends to polyhedral products, right? Polyhedral products sit inside the Cartesian product, so that doesn't come as a great surprise. But here, the automorphism group of the simplicial complex is a subgroup of the symmetric group. Now, it's not the full symmetric group because it has to take simplices to simplices, right? So the automorphism group is a subgroup of the symmetric group. If the simplicial complex is the whole simplex, of course, then the automorphism group is the symmetric group. So in this case here, this is our Cartesian product of x's, remember, went to the j of, and so the version of what I just had on the screen for Cartesian products, this is the version for polyhedral products, right? It's exactly the same, exactly the same. And the non-trivial result, which looks rather innocuous, is that this map here is equivariant with respect to the action of the automorphism group of the simplicial complex. Now that turns out to be a bigger deal than I can understand, but it's quite a big deal. Okay, so that is Al-Raisi's theorem there. Now, let's continue the story, right? We know that J of y is the same as loop suspension of y, so I can just suspend that map, right? And then there is an evaluation map. And what does that evaluation map do? Well, it evaluates a loop at the suspension parameter. So if the suspension parameter is t and the loop is f, it evaluates f at t, evaluation map. And it takes me back to y. Now, this map is not equivariant. If y has a g action on it, this map, the evaluation map following this James construction map, that is not equivariant. But it is equivariant in cohomology, right? It is equivariant in homology. Now, so this says I can replace the suspension of j of y with the suspension of y, and that's what I do, right? Remember, here we had j of all of this. I do that to it, and this takes me, this looks very familiar, right? Because that is exactly the splitting which I described for polyhedral products, right? And I'm applying cohomology to both sides, remember? it's the same as taking this and applying E star here and E star there, right? That's what that line says, right? So the miracle is that this map in cohomology, in homology, is equivariant with respect to the automorphism group of the simplicial complex, right? That's fairly surprising. That's very surprising, right? Because this wedge product is quite a big jumble. So the fact that this is true surprises me. Okay, well, so what? Well, continuing, let's now restrict to the special case where the simplicial complex is the boundary of the n-gon, what Fred and his student call a necklace, right? The boundary of an n-gon. Now, the automorphism group of the boundary of the n-gon is the dihedral group of order 2n. Now, sitting inside the dihedral group is the cyclic group of order n. Cn is the cyclic group of order n, and it sits inside the automorphism group. So now, that means that the cyclic group is acting on the cohomology of this. In particular, it acts on H2 of the cohomology of that. So it's a representation, right? It's acting on H2 of the cohomology of this particular polyhedral product. Now you remember, these were the surfaces of genus, whatever that genus was, according to Coxeter's theorem. So we are looking at the cohomology, the second cohomology of the suspension of the surface of genus G, and we're looking at it under the action of a cyclic group, and that cyclic group is a subgroup of the group of automorphisms of the necklace, of the boundary, right? And what we do is, if you look at the basis elements in the group ring here, right? The basis elements, sorry, I beg your pardon. If you look at the basis elements in here, and then look at the orbits of the Cn action, and count the number of orbits. So you're just counting the number of orbits on basis elements, right? That's all you're doing. And you get this number. Well, Al-Raisi gets this number, which has contained in it the Euler phi function, right? So that's pretty interesting. I mean, that's interesting right there. So just remember, this came from the James construction and the stable splitting of a polyhedral product. And now we have, holding in our hands, the Euler phi function. So that's got to be interesting, even if one like me, you don't know what's going on. That is certainly very interesting, right? Well, it gets better than that, in fact. So he counts these orbits. He counts, now remember, I'm reporting on his work, so I'm not so intimate with it. But he counts those orbits by counting inequivalent two colorings of an M-beaded necklace. Now, I should have taken Fred's advice, included a picture of this. But if you look at the boundary of the polygon, the n-gon, and you just color the vertices in two colors, and you want to count the inequivalent different ways of coloring with two colors, then that's how he proved the theorem. But he can count the orbits in a completely different way by a method with which I'm not familiar, but this method uses what are called primitive necklaces. And if you count those orbits under that action of the cyclic group, which is a subgroup of the group of automorphisms of the simplicial complex, and you're doing this calculation using that stable splitting, right? That's where the information is coming from. Lo and behold, you get another expression that involves the Mobius function. So it turns out those two numbers have to be the same, right? So here is an identity which I think surprised many people. Here is an identity identifying the Mobius involving the Mobius function and the Euler phi function. So that's not bad, not a bad theorem for a thesis so far, right? So that's
and evens or
sorry?
you need and even?
No, I don't. There was a GCD condition earlier.
Because you have these two columns.
Yeah, I don't think n doesn't have to be even. 5 gone. Works for...
Two columns does not mean that.
No, the vertices have to be 2 different colors. The vertices have to be 2 different colors.
But the size don't.
Yeah, does size, as far as I know, the size doesn't matter, no. Okay, so that's one part of the work that Fred was going to talk about. Now, also, the cyclic group acts on this surface. Remember, the cyclic group is a subgroup of the group of automorphisms of Kn. And now you can ask questions about what is this quotient, right? So this is a closed surface of genus G, and you can ask yourself, what is this quotient, right? Well, the one thing of which you can be certain is it's not going to be a smooth manifold. But of course it is a smooth manifold. The map this is a finite branch cover, and the quotient is a closed surface. It's smooth, not in all cases, right? It says examples exist where the quotient by the full automorphism group is not a closed manifold, right? But it is, and here's an example. I think I included an example for you. Yes, if you just take the 6-gon, and so that gives me, I've forgotten what the genus of the surface is, the original surface, but once you mod out by this a group of automorphisms, you get a surface of genus 2, right? Now, maybe if you can test your geometric intuition by whether that's obvious to you or not, right? But I can't, off the top of my head, I couldn't see it. And how does he prove that you get a smooth surface? Oh, by the way, an analogous results fails for our friend, the one that we use in toric geometry, D2S1. It's not true in that case. You need D1S0. And the way he proves it is he looks at the polyhedral product, a piece of the polyhedral product that corresponds to a maximum face. So that's just a Cartesian product, right? Just a Cartesian product. And there he shows explicitly that each point, that it's a sort of fundamental domain for the action, and each point in the quotient space has got an open neighborhood homeomorphic to R2. He just does that explicitly. He tests every case. So that's the gist of his work, which I found very surprising. Okay, now I want to switch gears. I'm going to change the subject that I'm talking about somewhat. So I finished discussing the very interesting work of Fred's students, and I hope I did justice to his work. Okay, now I want to go to a project that the 4 of us have been working on, and that is to do with the cohomology of these polyhedral products, right? So you have a polyhedral product. It's a natural subspace of the Cartesian product, and you can ask, well, what are the cohomology groups of this topological space? Well, we know that even in the case of D2S1, the cohomology of the moment angle manifold is a very complicated gadget, right? So it's very easy to go in to challenge somebody and say, tell me what the cohomology is on the nose, right? And you might be confronted with a blank stare. So this is an effort to describe the cohomology rings of polyhedral products. And how are we going to do that? Well, we take a simplicial complex and we order the simplices in the simplicial complex by left lexicographical ordering of the vertices. You take a simplicial complex and you order the simplices in the simplicial complex, right? You write them down in order. So there is an ordering, right? The first simplex, the second simplex, the third simplex, right? You order them. And then you filter the polyhedral product. The teeth filtered part will be the union of the Cartesian products which correspond to those simplices which have weight less than or equal to t, right? So you're not making the whole polyhedral product, you're just making part of it. Well, I think I have an example here for you. So if I take the example here of a simplicial complex which is the one simplex. Now, if a simplicial complex is the one simplex, right, then the polyhedral product is just x1 cross x2, right? There are no A's because there's only one simplex, right? So one maximal simplex. So in this case, the polyhedral product is this x1 cross x2. Well, what is the filtration? Well, according to the ordering that I've chosen up there, the lexicographical ordering, the first piece is just A1 cross A2. The second piece is X1 cross A2, so I've jazzed this up. Then the third piece is I add this over here, and then finally the fourth piece is the whole thing. So that's a trivial filtration, just comes from ordering the simplices in a simplicial complex. You don't think you're going to get much mileage out of that. Right, well, where there's a filtration in homotopy theory, you know the expression, well, where there's a filtration, you've got a calculation coming up, right? So we want to make the polyhedral product by adding one simplex at a time. Adding one simplex at a time, right? But you can't do that, right? You can't do that because the polyhedral products have different lengths until you get the idea of having ghost vertices. Now, when Taras first told me about ghost vertices, you know how you remember some things in the past to make you cringe. And the thing I said dismissing the idea, I'm very embarrassed about. But by using ghost vertices, we can compare these things, right? The ghost vertices just contribute A's for the missing vertices, right? Missing the objects that are not vertices. Okay, so if I can consider every simplex as having vertices which lie in the set 1 to m, right? So if it's only got n plus 1 vertices, then the rest of them are what are called ghost vertices. And a result of Jelena and Stephen tells us what happens if you make a polyhedral product by adding one simplex at a time. Now look, the polyhedral product is indexed by a simplicial complex, right? So you might ask the question, well, what happens if I make the polyhedral product by adding a simplex and watching it grow, right? But it's not easy to add a simplex. The definition stops you from adding a simplex unless you get this idea of using ghost vertices, so everything has the same number of vertices. Okay, well, there is a diagram of cofibrations where the top, if you look at the top left, that is the polyhedral product for the boundary of the simplex you are adding. The next one is the polyhedral product you're making, the full simplex, and then C is the cofiber of that map. Remember, we have ghost vertices. We have ghost vertices, right? It turns out, and the bottom is the whole polyhedral product. So I'm moving from filtration S-1, I'm adding the S simplex to move to the S filtration. And it turns out that this diagram allows us to identify the filtered quotients, right, from that cofibration sequence, because the top row is a completely standard object, right? The top row is a completely standard object. It's the bottom row about which we want information. Well, there is a spectral sequence for any cohomology theory. I've just told you the filtration. When you have a filtered space under suitable conditions, that makes a spectral sequence, right? And the spectral sequence can be used to compute the cohomology. Now, only if you can identify the E1 term, well, the E1 term of our spectral sequence are the cohomology groups of these quotients, direct product with these missing ones. These are the ones that come from the ghost vertices. And these are the ones that belong to the honest simplex. Now, we do not work with this half-smash product. We work with the smash moment angle complexes because we use the splitting to work out the cohomology ring, not just the additive structure. Even though it's a stable splitting, you can work out what the cup product is. Now, that's counterintuitive, but it's a fact. Okay, so the one term of the spectral sequence is this gadget here, and the key fact is that the differentials in these spectral sequences are always computable. It doesn't matter what x and a are, you can always compute the differential. Okay, well, I should mention here that Xibing Zheng, who's with us here, he has a description of the cohomology of polyhedral products as well, right? But our methods are distinct from his, and our presentation is quite different. And I noticed that Xibing is speaking Sunday at 11:40, and he will at that time describe his approach to this same problem. Okay, but it's not. The approaches are different. Now, without working out any differentials, right? We've got a spectral sequence. You have to work out differentials to get information, but without doing any differentials, no differentials, you immediately get Coxeter's result in the example of an n-gon, because you can compute the Euler characteristic of E1. E1 was made from the cohomology of x mod a's, right? And the cohomology of a's. So you can just go through and work out the Euler characteristic. The Euler characteristic does not change under differentials. So you get Coxeter's result even before you've bothered to work out any differential at all. And another result is if you have CW pairs so that the cohomology of x maps onto the cohomology of y, you get a Stanley-Reisner object. Here's a Stanley-Reisner object for any x and a, not just disks and circles, or right? For any x and a's, a Stanley-Reisner object answer. Under suitable free, this one works over the integers, but normally most of our calculations require freeness condition. And that works over any cohomology theory where that's split short exact and free. In particular, ordinary cohomology with field coefficients. Now, I just want to make some general remarks about the spectral sequence. The first key point is that the spectral sequence splits into two parts. Now, this is very surprising. The spectral sequence splits into two parts. One part has no differentials, and the other part does have differentials. But the other part computes the cohomology of a polyhedral product which you know by the wedge lemma. So you know the answer. Well, if you know the answer, you know all the differentials, right? So either way, we don't have to compute any differentials. But I mean, the technology is very complicated. But this is the basic idea. This is the reason you can get answers. One part has no differentials, and the part that does have differentials, its answer is given by the wedge lemma. You know its cohomology. Now, it all boils down to knowing the cohomology of zk of d1s0. It doesn't matter what x and a are. It doesn't matter what x and a are. Everything boils down to the case of d1s0. Because you're looking at cones on stuff, and that always involves d1s0. And under suitable freeness conditions, this is a short lecture, so I really can't go into it. The ring structure is described in terms of products among the kernels, images, and co-kernels of the xi's, ai's, and x, and also the product in here as described by the stable splitting. Now, Fred, Martin, Sam, and I, we wrote a paper which showed how you get the cup product in polyhedral products from the stable splitting. And so if you take that description, these are the two ingredients that in which the answer is presented. Now, that I was going to tell you about free loop spaces, so I'll just say free loop spaces. And that's about all I can say about it. Well, again, thank you for this opportunity. I hope I've done Fred's justice, and I hope I've given you a little insight into the things that a group of us have been working on. And thank you very much for your